Professor Einstein's theory. There exists an enormous literature devoted to the exposition, explanation, popularization, criticism and elaboration of the principles of Einstein, but owing to the close relationship between the theory of relativity and mathematical physics, deductions from this theory are difficult to formulate logically. The fact must be accepted that neither Professor Einstein himself, nor any of his numerous followers and interpreters have succeeded in explaining the meaning and essence of his theories in a clear and comprehensible way. Mr. Bertrand Russell points out one of the first reasons for this fact in his book, The ABC of Relativity. He writes that the name, theory of relativity, misleads people and that a tendency to prove that everything is relative is generally ascribed to Professor Einstein, while in reality he endeavors to discover and establish that which is not relative. It would be still more correct to say that Professor Einstein endeavors to establish the relation between what is relative and what is not relative. Professor Troelsen, in his textbook of physics, writes of the theory of relativity, see Volume 5, page 350. The foremost place in Einstein's theory of relativity is occupied by a perfectly new and at first glance incomprehensibly strange concept of time. Much effort and prolonged work on oneself are required to become used to it. But it is infinitely more difficult to accept the numerous consequences that follow from the principle of relativity, and affect all branches of physics without exception. Many of these consequences obviously contradict what is usually, though often without adequate motive, called common sense. Some of these may be called the paradoxes of the new doctrine. Einstein's ideas about time may be formulated as follows. Each of two systems moving relative to one another has in fact its own time, perceived and measured by an observer moving with the particular system. The concept of simultaneity in the general sense does not exist. Two events, that occur at different places, may appear simultaneous to an observer at one point, whereas for an observer at another point they may occur at different times. It is possible that for the first observer the same phenomenon may occur earlier, and for the second, later. Per Professor Troelsen. Further, of the ideas of Professor Einstein, Troelsen singles out the following. The ether does not exist. The concept of space, taken separately, has no meaning whatsoever. Only the coexistence of space and time make reality. Energy possesses inert mass. Energy is an analog of matter, and the transformation of what we call the mass of ponderable matter into the mass of energy, and vice versa, is possible. It is necessary to distinguish the geometrical form of a body from its kinetic form. The last points to a definite connection between Einstein's theory and the supposition of Fitzgerald and Lorentz, as to the lengthwise contraction of moving bodies. Einstein accepts this supposition, although he says that he bases it upon other principles than those of Fitzgerald and Lorentz, namely on the special principle of relativity. At the same time, the theory of the lengthwise contraction of bodies, deduced not from facts but from Lorentz's transformations, becomes the necessary foundation for the theory of relativity. In making use exclusively of Lorentz's transformations, Einstein affirms that a rigid rod, moving in the direction of its length, is shorter than the same rod when it is in a state of rest, and the more quickly the rod moves, the shorter it becomes. Hence a rod moving with the velocity of light would lose its third dimension, it would become a cross-section of itself. Lorentz himself affirmed that an electron actually disappeared when moving with the velocity of light. These affirmations cannot be proven, since the contractions, even if they really occur, are too negligible with all possible velocities. A body moving with the velocity of the Earth, i.e. 30 km per second, must according to the calculations of Lorentz and Einstein, undergo contraction by 1/200,000th of its length. That is, a body 200 meters long would contract by 1 millimeter. Further, it is interesting to note that the supposition as to the contraction of a moving body radically contradicts the principle established by new physics of the increment of energy and mass in a moving body. This latter principle is perfectly correct, although it is yet to be elaborated upon. As we shall see later, this principle in its full meaning, which is as yet unrevealed in new physics, is one of the foundations of the new model of the universe. Passing to Einstein's own exposition of his fundamental theory, we see that it consists of two principles of relativity, the special principle and the general principle. The special principle of relativity is supposed to establish the possibility of examining together, and on the basis of a general law, facts of the general relativity of motion that appear from the ordinary point of view to be contradictory. Or to speak more accurately, the fact that all velocities are relative, and that at the same time the velocity of light is non-relative, limiting and maximal. Einstein finds a way out of the difficulty created by all of this, first by understanding time itself, according to the formula of Minkowski, as an imaginary quantity, resulting from the relation of the given velocity to the velocity of light. Second, by making a whole series of altogether arbitrary assumptions on the borderline of physics and geometry. Third, by replacing the direct investigation of physical phenomena, and the observation of their correlations, by purely mathematical operations with the help of Lorenz's transformations, the result of which show, in his opinion, the laws governing physical phenomena. The general principle of relativity is introduced where it becomes necessary to make the idea of the infinity of spacetime agree with the laws of the density of matter, and the laws of gravitation in the space accessible to observation. To put it briefly, the special and the general principles of relativity are necessary for agreement between contradictory theories on the borderline of old and new physics. The fundamental tendency of Einstein is to regard mathematics, geometry, and physics as one whole. The principle is certainly quite correct as the three ought to constitute one. But ought to constitute does not mean that they do constitute. The confusion of these two concepts is the chief defect of the theories of relativity. In his book, Relativity, the Special and General Theory, published by Methuen and Company London, on pages 55, 56, and 57, Professor Einstein writes, "Space is a three-dimensional continuum. Similarly, the world of physical phenomena, which was briefly called the world by Minkowski, is naturally four-dimensional in the spacetime sense. For it is composed of individual events, each of which is described by four numbers, namely three space coordinates, and a time coordinate. That we have not been accustomed to regard the world in this sense, as a four-dimensional continuum, is due to the fact that in physics, before the advent of the theory of relativity, time played a different and more independent role, as compared with the space coordinates. It is for this reason that we have been in the habit of treating time as an independent continuum. As a matter of fact, according to classical mechanics, time is absolute, i.e. it is independent of the position, and the condition, of motion of the system of coordinates. The four-dimensional mode of consideration of the world is natural in the theory of relativity, since according to this theory, time is robbed of its independence. However, the discovery of Minkowski, which was of importance for the formal development of the theory of relativity, does not lie here. It is to be found rather in the fact of his recognition that the four-dimensional spacetime continuum of the theory of relativity, in its most essential formal properties, shows a pronounced relationship to the three-dimensional continuum of Euclidean geometrical space. In order to give due prominence to this relationship, however, we must replace the usual time coordinate t by an imaginary magnitude the square root of -1, multiplied by ct proportional to it. Under these conditions, the natural laws satisfying the demands of the special theory of relativity assume mathematical forms, in which the time coordinate plays exactly the same role as the three space coordinates. Formally, these four coordinates correspond exactly to the space coordinates in Euclidean geometry. The formula, the square root of -1, multiplied by ct, means that the time of every event is taken not simply by itself, but as an imaginary quantity in relation to the velocity of light, i.e. that a purely physical concept is introduced into the presumed metageometrical expression. The time duration t is multiplied by the velocity of light c and by the square root of -1, which without changing the magnitude, makes it an imaginary quantity. This is quite clear. But what is necessary to note in relation to the passage quoted above, is that Einstein regards Minkowski's world as a development of the theory of relativity, whereas in reality the special principle of relativity is built upon the theory of Minkowski. If we suppose that the theory of Minkowski is derived from the principle of relativity, then again, just as in the case of the theory of Fitzgerald and Lorentz, relating to the lengthwise contraction of moving bodies, it remains incomprehensible on what basis the principle of relativity is actually built. In any case, the building of the principle of relativity requires specially prepared material. In the very beginning of his book, Professor Einstein writes that in order to make certain deductions from the observation of physical phenomena agree with one another, it is necessary to revise certain geometrical concepts. Geometry means land measuring, he writes on the physical nature of space. Both mathematics and geometry owe their origin to the need to know something of the properties of things. On the basis of this, Professor Einstein considers it possible to supplement geometry, that is, for instance, to replace the concept of straight lines by the concept of rigid rods. Rigid rods are subject to changes under the influence of temperature and pressure, etc. They can expand and contract. All this must of course greatly alter geometry. Geometry, which has been supplemented in this way, is obviously a natural science, says Einstein on the physical nature of space, and is to be treated as a branch of physics. Special importance on the importance of the view on geometry expounded here is emphasized, because without it, it would have been impossible to construct the theory of relativity. Euclidean geometry must be abandoned. The next important point in Einstein's theory is his justification of the mathematical method he applies. Experience has led to the conviction, he says, that on the one hand, the principle of relativity, in the restricted sense, the principle of the relativity of velocities in classical mechanics, holds true. And that on the other hand, the velocity of the transmission of light in vacuo has to be considered to be a constant. See Relativity, page 42. According to Professor Einstein, the combination of these two propositions supplies the law of transformation for the four coordinates, determining the place and time of an event. He writes, "Every general law of nature must be so constituted that it is transformed into a law of exactly the same form, when instead of the spacetime variable of the original coordinate system, we introduce new spacetime variables of another coordinate system. In this regard, the mathematical relation between the magnitudes of the first order and the magnitudes of the second order is given by the Lorentz transformation. Or in brief, general laws of nature are covariant with respect to Lorentz transformations." See Relativity, page 42. Einstein's assertion that the laws of nature are covariant with Lorentz's transformation is an illustration of his position. Starting from this point, he considers it possible to ascribe to phenomena the changes that he finds in transformations. This is precisely the method of mathematical physics, condemned long ago, that was mentioned by Professor Troelsen in the passage previously quoted. In the theory of relativity, there is a chapter under the title, Experience and the Special Theory of Relativity. To what extent is the special theory of relativity supported by experience? This question is not easily answered, writes Professor Einstein in Relativity, on page 49. The special theory of relativity has crystallized out from the Maxwell-Lorentz theory of electromagnetic phenomena. Thus all facts of experience that support the electromagnetic theory also support the theory of relativity, see page 49. Professor Einstein acutely feels the need to establish the facts for his theorem upon firm ground. However, he succeeds in finding these facts only with respect to invisible quantities, electrons and ions. He writes, "Classical mechanics required to be modified before it could come into line with the demands of the special theory of relativity. For the main part, however, this modification affects only the laws of rapid motion, in which the velocities of matter are not very small as compared with the velocities of light. We have experience of such rapid motions only in the case of electrons and ions. For other motions, the variations from the laws of classical mechanics are too small to make themselves evident in practice." See page 44. Passing to the general theory of relativity, Professor Einstein writes, "The classical principle of relativity, relating to three-dimensional space with the coordinate of time t, a real quantity, is violated by the fact of the constant velocity of light. But the fact of the constant velocity of light is violated by the curvature of a ray of light in gravitational fields. This requires a new theory of relativity, and a space determined by Gaussian coordinates, applicable to non-Euclidean continua. Gaussian coordinates differ from the Cartesian by the fact that they can be applied to any kind of space, independently of the properties of that space. They adapt themselves automatically to any space, whereas Cartesian coordinates require space of special definite properties, i.e. geometric space. In continuing the comparison of the special and the general theories of relativity, Professor Einstein writes, "The special theory of relativity has reference to domains in which no gravitational field exists. In this regard, a rigid body in the state of motion serves as a body of reference, i.e. a rigid body the state of motion of which is so chosen that the proposition of the uniform rectilinear motion of isolated material points holds relative to it." See page 98. In order to make clear the principles of the general theory of relativity, Einstein takes the spacetime domain as a disk, uniformly rotating around its center, on its own plane. An observer situated on this disk regards the disk as being at rest. He regards the force acting upon him, and generally upon all bodies that are at rest in relation to the disk, as the action of the gravitational field. The observer performs experiments on his circular disk, with clocks and measuring rods. In so doing, it is his intention to arrive at exact definitions for the signification of time and space data, with reference to the circular disk. To start with, he places one of two identically constructed clocks at the center of the circular disk, and the other on the edge of the disk, so they are at rest relative to it, see page 80. Thus on our circular disk, or to make the case most general, in every gravitational field, a clock will go more quickly or less quickly, according to the position in which the clock is situated, at rest. For this reason it is not possible to obtain a reasonable definition of time, with the aid of clocks that are arranged at rest with respect to the body of reference. A similar difficulty presents itself when we attempt to apply our earlier definition of simultaneity in such a case, see page 81. The definition of the space coordinates presents insurmountable difficulties. If the observer, moving with the disk, applies his standard measuring rod, a rod which is short as compared with the radius of the disk, tangentially to the edge of the disk, then the length of the rod will be less, since moving bodies suffer a shortening in the direction of motion. On the other hand, the measuring rod will not experience a shortening in length, if it is applied to the disk in the direction of the radius, see page 81. For this reason non-rigid, elastic reference bodies are used, which are as a whole not moving in any way whatsoever, but which also suffer alterations in form ad lib, during their motion. Clocks, for which the law of motion is of any kind, however irregular, serve for the definition of time. We have to imagine each of these clocks fixed at a point on the non-rigid, elastic reference body. These clocks satisfy only the one condition, that the readings which are observed simultaneously on adjacent clocks in space, differ from each other by an infinitely small amount. This non-rigid, elastic reference body, which might appropriately be termed reference mollusk, is in the main equivalent to a Gaussian four-dimensional coordinate system, chosen arbitrarily. That which gives the mollusk a certain comprehensiveness, as compared with the Gauss coordinate system, is the really unjustified, formal retention of the separate existence of the space coordinates, as opposed to the time coordinate. Every point of the mollusk is treated as a space point, and every material point that is at rest relative to it, is at rest so long as the mollusk is considered as a reference body. The general principle of relativity requires that all these mollusks can be used as reference bodies, with equal right and equal success in the formulation of the general laws of nature. The laws themselves must be quite independent of the choice of mollusk, see page 99. In respect of the fundamental question as to the form of the world, Professor Einstein writes, "If we ponder the question as to how the universe, considered as a whole, is to be regarded, the first answer that suggests itself is surely this: as regards space and time, the universe is infinite. There are stars everywhere, so that the density of matter, although extremely variable in detail, is nevertheless on the average everywhere the same. In other words, however far we might travel through space, we should find everywhere an attenuated swarm of fixed stars of approximately the same kind and density, see page 105. This view is not in harmony with the theory of Newton. The latter theory rather requires that the universe should have a kind of center, in which the density of the stars is at a maximum, and that as we proceed outwards from the center, the group density of the stars diminishes, until finally, at great distances, it is succeeded by an infinite region of emptiness. The stellar universe ought to be a finite island in the infinite ocean. See pages 105 and 106. The reason why an unbounded universe is impossible is that according to the theory of Newton, the intensity of the gravitational field at the surface of a sphere filled with matter, even if this matter is of a very small density, would increase with the increasing radius of the sphere, and would ultimately become infinite, which is impossible. See page 106. The development of non-Euclidean geometry led to the recognition of the fact that we can cast doubt on the infiniteness of our space, without coming into conflict with the laws of thought or with experience. See page 108. Admitting the possibility of similar conclusions, Einstein describes the world of two-dimensional beings on a spherical surface. In contrast to ours, the universe of these beings is two-dimensional. But like ours, it extends to infinity. See page 108. This surface of the world of two-dimensional beings would constitute space for them. This space would possess very strange properties. If the spherical surface beings were to draw circles in their space, that is on the surface of their sphere, these circles would increase up to a certain limit and then would begin to decrease. The universe of these beings is finite, and yet has no limits. See page 109. Einstein comes to the conclusion that the spherical surface beings would be able to determine that they are living on a sphere, and might even find the radius of this sphere, if they were able to examine a sufficiently great part of the surface. But if this part is very small indeed, they will no longer be able to demonstrate that they are on a spherical world, and not on a Euclidean plane. For a small part of a spherical surface differs only slightly from a piece of a plane of the same size. See page 110. Thus if the spherical surface beings are living on a planet, of which the solar system occupies only a negligibly small part of the spherical universe, they have no means of determining whether they are living in a finite, or an infinite universe. Because the piece of universe to which they have access, is in both cases practically plane, or Euclidean. See page 110. To this two-dimensional sphere universe there is a three-dimensional analogy, namely the three-dimensional spherical space, which was discovered by Riemann. Its points are likewise all equivalent. It possesses a finite volume that is determined by its radius. See page 111. It is easily seen that the three-dimensional spherical space is quite analogous to the two-dimensional spherical surface. It is finite, that is of finite volume, and has no bounds. See page 112. It may be mentioned that there is yet another kind of curved space, elliptical space. It can be regarded as a curved space, in which the two counterparts are identical. An elliptical universe can thus be considered to some extent as a curved universe, possessing central symmetry. See page 112. It follows from what has been said that closed spaces without limits are conceivable. From amongst these, the spherical space, and the elliptical excels in its simplicity, since all points in it are equivalent. As a result of this discussion, a most interesting opinion arises for astronomers and physicists. That is, whether the universe in which we live is infinite, or whether it is finite in the manner of the spherical universe. Our experience is far from being sufficient to enable us to answer this question. But the general theory of relativity permits of our answering it with a moderate degree of certainty, and in this regard the difficulty mentioned earlier, from the point of view of the Newtonian theory, finds its solution. See page 112. The structure of space according to the general theory of relativity differs from that generally recognized. According to the general theory of relativity, the geometrical properties of space are not independent, but are determined by matter. Thus we can draw conclusions about the geometrical structure of the universe only if we base our considerations on the state of the matter as being something that is known. We know from experience that the velocities of the stars are small, as compared with the velocity of the transmission of light. We can thus, as a rough approximation, arrive at a conclusion as to the nature of the universe as a whole, if we treat the matter as being at rest. See page 113. We might imagine that, as regards geometry, our universe behaves analogously to a surface that is irregularly curved in its individual parts, but which nowhere departs appreciably from a plane. Something like the rippled surface of a lake. Such a universe might fittingly be called a quasi-Euclidean universe. As regards its space, it would be infinite. But calculation shows that in a quasi-Euclidean universe the average density of matter would necessarily be nil. Thus, such a universe could not be inhabited by matter everywhere. It would present to us an unsatisfactory picture, see page 114. If we are to have in the universe an average density of matter, which differs from zero, however small may be that difference, then the universe cannot be quasi-Euclidean. On the contrary, the results of calculation indicate that if matter be distributed uniformly, the universe would necessarily be spherical, or elliptical. Since in reality the detailed distribution of matter is not uniform, the real universe will deviate in individual parts from the spherical, i.e. the universe will be quasi-spherical. But it will be necessarily finite. In fact, the theory supplies us with a simple connection between the space expanse of the universe and the average density of matter in it, see page 114. Professor A.S. Eddington treats the last proposition in a somewhat different manner in his book, Space, Time and Gravitation. After mass and energy there is one physical quantity that plays a very fundamental part in modern physics, known as action. Action here is a very technical term, and is not to be confused with Newton's action and reaction, which is determined as energy multiplied by time, per Trolson. In the relativity theory in particular, this seems in many respects to be the most fundamental thing of all. The reason is not difficult to see. If we wish to speak of the continuous matter present at any particular point of space and time, we must use the term density. Density multiplied by volume in space gives us mass, or what appears to be the same thing, energy. However, from our spacetime point of view, a far more important thing is density multiplied by a four-dimensional volume of space and time. This is action. The multiplication by 3 dimensions gives mass or energy. The fourth multiplication gives mass or energy multiplied by time. Action is thus mass multiplied by time, or energy multiplied by time, and is more fundamental than either. Action is the curvature of the world. It is scarcely possible to visualize this statement, because our notion of curvature is derived from surfaces of 2 dimensions in a 3-dimensional space, and this gives too limited an idea of the possibilities of a 4-dimensional surface, in a space of 5 or more dimensions. In 2 dimensions there is just one total curvature, and if that vanishes, the surface is either flat or at least can be unrolled into a plane. Wherever there is matter there is action, and therefore curvature. It is interesting to notice that in ordinary matter, the curvature of the spacetime world is by no means insignificant. For example, in water of ordinary density, the curvature is the same as that of space in the form of a sphere, of radius 570 million kilometers. The result is even more surprising if expressed in time units. The radius is about half an hour. It is difficult to picture quite what this means. But at least we can predict that a globe of water of 570 million kilometers radius would have extraordinary properties. Presumably there must be an upper limit to the possible size of a globe of water. As far as can be determined, a homogeneous mass of water about this size, and no larger, could exist. It would have no center and no boundary, every point of it being in the same position with respect to the whole mass as every other point of it, like points on the surface of a sphere with respect to the surface. Any ray of light, after traveling for an hour or two, would come back to the starting point. Nothing could enter or leave the mass, because there is no boundary to enter or leave by. In fact, it is coextensive with space. There could be no other world anywhere else, because there isn't an anywhere else. See pages 147 and 148. An exposition of the theories of new physics that stand apart from relativity would take too much space. The study of the structure of light and electricity, the study of the atom, the theories of Bohr and particularly the study of an electron, quantum theory, lead physics along entirely right lines. If physics really succeeded in freeing itself from the aforementioned impediments, which arrest its progress, and also from unnecessarily paradoxical theories of relativism, it would someday discover that it knows much more about the true nature of things than might be supposed. Old physics. Geometrical conception of space, that is, consideration of space apart from time. Conception of space as emptiness, in which there may or may not be bodies. One time for all that exists, time measurable on one linear scale. Aristotle's principle of the constancy and unity of laws in the whole universe, and as deduction from this principle, confidence in immutability of recognized phenomena. Elementary understanding of measure, measurability, and incommensurability. Measures taken for everything from outside. Recognition of a whole series of concepts, difficult to define, such as time, velocity, etc. as primary concepts requiring no definition. Law of gravitation or attraction and extension of this law, to phenomena of falling or weight. Universe of flying balls, both in celestial space and inside an atom. Theories of vibrations, undulatory movements, etc. Tendency to interpret all phenomena or radiant energy by undulatory vibrations. Necessity of hypothesis of ether in some form or other. Ether a substance of greater density, and ether a substance of greatest rarity. New physics. Attempts to escape from three-dimensional space by means of mathematics and metageometry. For coordinates. Study of the structure of matter and of radiant energy. Study of the atom and study of electrons. Recognition of the velocity of light as limiting velocity. Velocity of light as universal constant. Definition of fourth coordinate in connection with velocity of light. Time as imaginary quantity. Minkowski. Recognition of the necessity for taking time together with space. Spacetime, four-dimensional continuum. New ideas in mechanics. Recognition of possible incorrectness of principle of conservation of energy. Recognition of possible transformation of matter into energy and vice versa. Attempts to build systems of absolute units of measure. Establishment of fact of weight of light and of materiality of electricity. New theories of structure of atom. Study of electron, quantum theory and the structure of radiant energy. Principles of increase of energy and mass of body in motion. Einstein's special and general principles of relativity. The idea of necessity for finite space in connection with laws of gravitation and distribution of matter in the universe. Curvature of spacetime continuum. Unlimited, but finite universe, measurements of which are determined by density of matter which constitutes it. Spherical or elliptical space. Elastic space. The mollusk of Einstein.